Please welcome to the stage Dr. Matt Turek.
Good afternoon. I'm Matt Turek, Deputy Director for DARPA's Information Innovation Office. Today, I'm going to talk to you about the current state of AI, and in particular, what it will take to get to trustworthy AI. Not just any sort of AI, but AI that you would trust your life with and not be foolish to do so. So we've seen amazing progress over the past decade. It's primarily been driven by machine learning, especially deep learning, leveraging enormous data sets and massive amounts of compute. And it's delivered results far beyond what we could have expected a decade ago. So I'm going to walk you through some of those really compelling AI capabilities. What you're seeing on this chart is year on the horizontal axis and required compute resources on the vertical axis. And it's worth noting, for that vertical axis, that's a log scale. So when you see a linear trend there, there's actually an exponential underneath that. So the first data point that I'm going to show you is something called generative adversarial networks, or GANs. These approaches optimize a two-player competitive game at the algorithm level. The generator creates data, and the discriminator tries to figure out if that data is real or not. This brought about revolutions in media synthesis and has driven a whole range of new approaches to machine learning training. The sorts of images that this technique was able to produce in 2014 were very fuzzy, as shown by the face on the slide. But now it's very difficult to tell if GAN-generated images are real or not. We've also seen significant progress in speech recognition. We've moved towards end-to-end neural networks, replacing hand-engineered approaches. These sorts of approaches can now handle noisy environments, accents, and multiple languages. It also takes less development time. And the results from these systems are competitive with human transcription on standard benchmarks. We've also seen huge progress in gameplay. Go is a game that's thousands of years old, and there's a huge number of board configurations, 10 to 172. Compare that to the number of atoms in the observable universe, which is about 10 to the 82nd. You'd have to square the number of atoms in the observable universe to cover the number of states available in Go as a game. DeepMind developed AlphaGo and used reinforcement learning and self-play approaches combined with observations of human games to build a compelling AI Go player. AlphaGo, that AI player, beat Lee Sedol, a world champion, in March of 2016. But it didn't stop there. AlphaGo Zero was developed, and in October of 2017, beat a whole bunch of previous versions of AlphaGo. The breakthrough here was it was done without any observation of human players. It took 3 days of training to get to the level of AlphaGo performance that beat Lee Sedol. In 40 days worth of training, it beat all previous versions of AlphaGo. We've also seen significant progress in game playing in poker. This is a long-standing AI challenge. So how is it different than Go? Well, in poker, there's deception involved and partial knowledge. The cards are hidden from the players, unlike Go, where you can observe the complete state of the game just by looking at the board. In January 2017, an AI algorithm called Libratus played 4 top-class human poker players pairwise. Over 100,000 hands, and it beat them decisively in that tournament. In July of 2019, Pluribus, another AI algorithm, played 5 human professionals across 10,000 hands of poker and won. And this time it wasn't playing pairwise, it was playing against the group of human professionals. Again, this approach leveraged self-play, learned a baseline strategy, and was able to improve that strategy during the tournament. We've also seen amazing progress in maybe more grounded real-world applications like self-driving cars. In October of 2020, Tesla released a beta version of their full self-driving, and that relies heavily on computer vision algorithms. I'll say more about that in upcoming slides. We've also seen huge progress in large language models, or what the community is now sometimes calling foundational models. These produce fluent-sounding text, and they're trained on massive amounts of data, essentially all non-code, non-obscene English language on the internet. And they've provided amazing capabilities: machine translation, text classification, question answering. These approaches are state-of-the-art in many tasks and benchmarks. And they leverage transformer models that have been adapted to vision and vision plus language and code plus language tasks. But the cost of training these models, one estimate for GPT-3 was $4.5 million to train it once. We've also seen significant progress in things like protein folding. This is a 50-year-old grand challenge. Proteins are large, complex molecules that are essential to life, and their behavior depends on their 3D structure, their shape when they change and fold. In November of 2020, AlphaFold was released, again developed by Google's DeepMind and leveraging some of the work on AlphaGo and AlphaGo Zero. AlphaFold predicts protein structures based on the sequence of amino acids. They've released an open database of over 200 million predictions that's publicly available. And the accuracy of these predictions rivals laboratory methods in a number of cases. So does that mean we're on the right track for trustworthy AI? We don't think so. Tesla, again, uses very sophisticated machine learning systems for self-driving. There's 48 neural networks in Tesla's system. They leverage 1,000 professional data labelers and over 1.5 petabytes worth of data. But still, self-driving cars fail, and sometimes catastrophically. And the humans are still held responsible when autopilot is engaged. There's been dozens of crashes into emergency vehicles with flashing lights and sometimes in the middle of the road. It's not just the failure, it's the mode of failure. We've seen AI systems, these large language models, also lack basic comprehension. They sound fluid, but if you ask something like GPT-3, which is heavier, a toaster or a pencil, the answer is a pencil, not a mistake that a human would make. These statistical models get tripped up by challenges like winnow ground. This was a new challenge developed explicitly to test model dependence on statistical correlation. So the way the task is formulated, there's two image and caption pairs, and they differ simply by word order. So in this case, it's a fire truck versus it's a truck fire. Two very different things, but simply a word swap. Vision language models on this task just do slightly better than chance, slightly better than random. Human performance is nearly 90%. You might ask, why is there that extra 10% gap? That turns out to be the gap between someone on Amazon Mechanical Turk and really exquisitely trained researchers who understand the semantics and pragmatics of language. But that 10% difference is essentially the span of human gap. These large language models are also not appropriate for everything. The arithmetic performance of these models is highly correlated with the number of examples that they've seen in their training data for specific digits. They're not learning generalizable arithmetic rules in most cases. And if you look at the results for multiplication, they're even worse than what we're showing here for addition and subtraction. So let me step back for a minute and remind you about two key phases of machine learning systems: training and testing. So the training phase starts with curated training data. That goes through a learning algorithm that comes up with an approximate model of the relationships between the supervision and the data. Deep learning has provided innovations in the learning process and the model representation that has driven many of the developments that we've seen recently in AI. After a system's been trained, we have runtime, or sometimes what we might call test time. So there we take sense data that's collected in the same way as the training data, because we know for many machine learning systems that statistical drift in the data can cause problems. So the model takes in the data, produces an output. It might be a classification where there's a set of particular buckets that we're putting the output into, or a prediction in terms of a floating point regression. Now, in the context of that training and testing process, there's a number of ways that you can attack the AI process. There are physical attacks that can modify the scene. And it's important to keep in mind the adversary always has access to the physical environment. This makes these attacks very challenging to deal with. And what's illustrated on the stop sign on this slide is one of the classics, putting a Post-it note or another type of sticker on a stop sign to change the perception of a machine learning system of that stop sign. There's also ways to create artifacts in the sensor chain that might push the data out of the training distribution. That can result in unexpected behavior from the machine learning system. You can also alter the training data that's collected for developing the system, particularly if that training data is collected in the wild where anyone can access it. There's also cyber means to attack AI systems. There's approaches where you can insert subtle noise perturbations into the sensor chain. Now, these won't fool humans. In fact, they're probably imperceptible to us, but they will completely fool many machine learning algorithms. You can use cyber means to alter the training data in a secure system, or alter the learning algorithm, or alter the model itself, for instance, by changing the weights of a neural network. We've also seen the drastic increase in compute necessary to produce state-of-the-art machine learning systems. What's shown on this slide is a result from the Center for Strategic and Emerging Technology, or CSET, at Georgetown University. This is a study on the compute costs of state-of-the-art AI systems. And essentially, it has dire implications. That cost is doubling every 3 to 4 months. And according to their calculations, the cost of building a state-of-the-art machine learning model will intersect the size of the US GDP in the late 2020s. Now, that might seem fanciful, but oftentimes improvement in machine learning models requires exponential increases in model size for a fixed amount of performance in the model. If you combine that with over-parameterization of the models, you get strongly exponential increases in model size and resulting cost for training it. So clearly, this trend is not sustainable. So how do we find other ways? One of the key questions here is, will industry solve this? DARPA doesn't need to do something that industry will already do. And it turns out that industry and DoD drivers are not well aligned in this space. In terms of data and compute, industry often has access to massive amounts of training data and large amounts of compute. From a DoD perspective, we often have much more limited data. We might not even have data for rare and unusual events. And those might be some of the events that we care the most about. Indications and warnings of adversary behavior, for instance. On the motivation side, industry is profit-driven. And that's okay. But what it allows them to do is have the flexibility to select which opportunities they're going to pursue. The DoD, on the other hand, is purpose-driven. We have less flexibility. We need to respond to threats, particularly ones that may not be of our choosing. And this can result in significant consequences. Again, from an industry perspective, they're oftentimes focused on low-hanging fruit, like making recommendations for purchases or for media. On the DoD side, we have significant consequences. These might be critical life or death decisions that may result. You heard from Hal Hebron earlier about the alias system and what happens when a neural network makes a deviation from the plan in the context of flying an autonomous system. There's also significant threats from a DoD perspective. Now, industry has to deal with commercial competitors, and that competition is intense. But from a DoD perspective, we have nation-state level adversaries. They have significant resources, they're willing to employ deception, and they have a desire to change our fundamental way of life. That can have a huge impact on our society. Now, of course, we want to leverage industry wherever applicable, but it's not likely to solve some of these core DoD problems. So where are we trying to go from a DoD perspective? Let me walk you through this pie chart, and I'm going to start in the upper right-hand corner. In the future, we want to have fluent, intuitive AI teammates. These are the sorts of systems that can anticipate what humans need, can communicate in multiple modalities, and do that in ways that are convenient for humans, in human native forms. They need to display emotional and cultural intelligence, and they need to be able to exercise discretion. These sorts of systems would never make stupid mistakes. They'd have more than 5 nines worth of reliability, and they'd be able to leverage the strengths of humans and AI systems. They'd be highly interactive and have introspectable representations that allow us to understand them. Agents that promote national security. These sorts of agents would help counter mis- and disinformation at scale and do it in a way that empowers individuals, encouraging pro-social and collaborative behavior, helping foster mental health, and perhaps challenges like suicide prevention. All of that would need to take social context into consideration. We also want AI systems that can accelerate the development of technology. These sorts of systems would synthesize understanding. They would suggest new paths that humans might not have thought of or seen before. They would accelerate the engineering design process, perhaps around things like CPUs or integrated cyber-physical systems, and would have applications in a wide variety of areas, from medicine to chemistry, materials science, and other engineering disciplines. We also ultimately want AI agents that support knowledge navigation. From a DoD perspective, these sorts of agents might provide strategic decision-making support, help with planning, command and control, situational awareness. They would need to work across multiple domains and integrate information at multiple scales. They would automatically surface relevant information and perhaps provide intelligent modeling and simulation at scale and speed, anticipating what questions the human might ask next, and would enable exploring counterfactuals quickly and easily. These sorts of systems would also respect privacy. And then finally, in terms of trustworthy autonomous agents, these would be focused on a wide range of mission-driven use cases, both defensive and offensive. And they might need to work in situations where the human is off the loop. For instance, in defensive cyber, where things happen faster than a human may be able to perceive and understand. But to have those sorts of trustworthy systems, they need to have quantifiable effects. Ideally, they would have superhuman performance and be highly adapted for tasks with task-specific sensors and actuators. But they'd also be able to learn and adapt flexibly in the context of new situations. They'd be effective in scenarios where there's limited communications and in the presence of adversaries. So what does it mean to be trustworthy? That's a really complex question. Researchers have debated this in the human-only case. And AI is even more nuanced. There's a well-studied model of trust from Mayer in 1995 that's got tens of thousands of citations. And it talks about 3 factors of influence on trust: ability, benevolence, and integrity. And we've adapted them here for AI-human interactions. So first is the ability to operate competently, mapping to ability. This is really what's received the most attention from the AI community. It's reflected in things like performance numbers, such as classification accuracy. That's become our proxy for trust in the AI community, but it's only a part of the puzzle. The second area is AI systems need to be able to interact appropriately with humans. This maps to benevolence in the human-driven model, because benevolence is really achieved via relationships between humans. So in this context, we need AI systems that can partner and team and are easy for humans to understand. How do we explain what we want to those sorts of systems, and how do they communicate back to us so we can understand their responses? In this context, their reasons may be more important than the answer itself. And third, we need AI systems that behave ethically and morally. There's been a lot of books written on this topic. It's really just the beginning. There's much remaining work to be done here, particularly in the context where lives are at risk from a national security standpoint. We need AI systems that can reason about ethics and morals. Now, we've been pushing ethics and morals into the development process. That's been a growing focus in the AI community, and I'll tell you a little bit more about some of DARPA's work in upcoming slides. But we need more than that. We need AI systems that can make decisions in alignment with humans. And again, that requires AI systems that can reason about ethics and morals. So what will it take to create trustworthy AI systems? We've been talking about it in terms of using the right model for the right job and doing that in a way that's intelligently integrated. And what I'm going to tell you about next is 3 thrust areas that need significant development in order to enable trustworthy AI. So the first is significant advancements in AI theory and foundational AI. We need to understand things like what problems are particularly hard. What are the limits of learning approaches? What's possible in low data regimes or in the conditions of rare or unusual events? Or in the face of adversary attacks? If we had fundamental understanding, that might help us understand the performance and the limits and provide guardrails for AI systems. The second thrust here is AI engineering. We need to stand up AI engineering as a discipline. Those theoretical foundations that I talked about are necessary to enable AI engineering as a discipline. And it requires rigorous design and evaluation processes. As you heard from other speakers, other disciplines have matured, particularly from bespoke trial and error processes, which is often the focus of how we build machine learning systems today, to scientifically well-founded and characterized engineering processes. It's time we do the same for AI. So what's required to have AI engineering as a discipline? We need to be able to decompose and recompose the design of intelligent systems. That implies foundational understandings of intelligence. We need to be able to predict the performance of AI systems across an expected range of operating conditions. And we need rigorous measurement processes to support that decomposition and recomposition process. What we have now often is a reliance on benchmarks, things like ImageNet, where it's been demonstrated that classifiers trained on ImageNet don't even generalize to another data set that is as close as humans can make to ImageNet. So these are all characteristics of existing mature engineering processes in other disciplines. Finally, human context. We need to be able to reduce the resources necessary to create and operate AI systems. We also need AI systems that can interact fluently with humans and that can reason about humans, build mental models of human behavior to understand and anticipate how humans may react. We are in the very early days of beginning to address these sorts of challenges. So now I'm going to start talking about some of the foundational work that we've been doing at DARPA in AI and give you some examples in these domains for programs. And their work cross-cuts these three foundational areas. So in terms of protecting AI systems against attack, DARPA's Guaranteeing AI Robustness Against Deception, or GUARD program, has been building defenses against adversarial attacks. And that program is considering multiple threat scenarios: the physical world, data poisoning, patch attacks. They're building theoretical foundations, developing empirical approaches to measurement, and developing principled techniques for much more rigorous testing. They've had some significant accomplishments in that program. They've assessed over 100 defenses from more than a dozen teams across audio, video, and multimodality settings. They've developed a new perception-based adversarial training method that's 2 times more robust against new attacks that were not seen during training. And they've developed new certified defenses for patch attacks. All of that is incorporated in an open source toolkit. Ultimately, GUARD is hoping to put significant foundations to underpin defenses against adversarial attacks. Kicking off early next year is the Assured Neurosymbolic Learning and Reasoning Program, or ANSWER. The goal of ANSWER is to guarantee the behavior of safety-critical systems. Now, ANSWER has a particular definition of what's trustworthy for a system. That system would be robust to domain-informed and adversarial perturbations. It'd be supported by an assurance framework that creates and analyzes evidence supporting safety and risk assessments. And the systems would be predictable with respect to specifications and models of fitness. This is really focused on that competent operation component that I described earlier. ANSWER's hypothesis is that Wave 3 AI approaches that combine neurosymbolic models will provide the performance of statistical Wave 2 approaches with the ability to assure brought by earlier symbolic approaches. So the example shown on this slide is a self-driving car running in a high-fidelity simulator. The purely symbolic approach results in a car that crashes on the training track and on a second track. The deep learning approach produces a vehicle and an algorithm that can drive the vehicle very quickly on the learning track. But when transferred to the new track, that system crashes. Highlights the brittleness of some of the machine learning-driven approaches. The combination in this context performs well on the training track and is robust on the new unseen track. Now, it might suffer some performance degradation, but it is able to successfully navigate the entire track. DARPA's Machine Common Sense program is building foundational understanding of the world. It has 2 core thrusts that underlie it. One is understanding how children learn, because children are the best learners on the planet. And the second is trying to mimic the reading capabilities of adults. One of the areas and one of the research teams on this program has been focused on developing and training their systems in simulation and then transferring to the real world. They're building algorithms that rely on proprioception, essentially monitoring the internal sensors of the robot. There are no hard-coded models of terrain or loads, and that gives the robot the ability to adjust to changing terrain and loads. So for instance, what you're seeing in the video is that bipedal robot being able to carry two loads that are shifting while it's moving dynamically. These sorts of systems are able to handle unexpected events and have real-world operational capabilities like helping soldiers carry loads in the field. The Symbiotic Design for Cyber Physical Systems program is developing techniques to explore massive design spaces. From a DoD perspective, that might be unmanned vehicles that can explore the Arctic or UAVs with very long flight time. The goal of the program is to rapidly explore the design space and develop designs that are correct by construction. Now, there's several core challenges that this program is going after: design space construction, design composition, exploring that design space, and doing it in conjunction with humans, such that there is a human interface that allows the engineers to explore the designs that the system recommends. This can help get humans out of our design comfort zone and explore systems that might provide breakthrough capabilities. The early results on that program has generated hundreds of designs that meet the specs for a particular task, but do it in out-of-the-box ways. In terms of building adaptable and resilient teammates, DARPA's Artificial Social Intelligence for Successful Teams, or ASSIST program, is focused on building some of those partnering foundations, developing a theory of mind and a theory of team, and ways to create interventions across the AI and human teams that improve team performance. They've created an experimental framework, an online environment that is looking at a simulated search and rescue task. They've explored that with over 100 three-person teams and had a variety of human and AI coaches that have suggested a variety of possible interventions. DARPA's Urban Reconnaissance through Supervised Autonomy, or URSA program, is developing capabilities to help situational awareness in urban combat environments. In particular, being able to understand threats. The program has looked at how do you probe the environment and measure human responses to discriminate subtle differences between hostiles and innocent people. And to support that program, the DARPA research team has embedded a legal, moral, and ethics team into the development process. That includes technologists, academics, ethicists, military, policy researchers, and the development team itself. Now, you might expect that that actually would just slow down and perhaps grind the development process to a halt. The result has actually been quite the opposite. By including that ethical development team, it forces developers to focus on hard challenges early instead of being surprised later. That program has also seen more effective capabilities, more effective operational capabilities as a result of including the LME team in the development process. This is similar to what we've seen on the Explainable AI program, whereby requiring explainability, we actually gained performance in a number of cases. DARPA's In the Moment program will be starting next year. ITM has several core goals: to identify human attributes that lead to trust in delegated decision-making. ITM hopes to model those attributes in a computational framework and then build them into algorithms that are more human-aligned. And finally, to develop quantitative ways for measuring the alignment between those algorithms and a reference group of humans. This is all going to be done in the context of DoD-relevant triage scenarios where the decision maker may be faced with limited options and life and death consequences. So I've sketched out an approach for how to get to trustworthy AI, in particular, 3 areas around theory, engineering, and human context. But there's much more to be done here. And we need your ideas to help make trustworthy AI possible. We want to include a broad and diverse pool of researchers. So I encourage you, reach out to PMs. They may ask you to submit an abstract, a white paper, or perhaps even a proposal. There are ways to participate in ongoing programs by attending PI meetings, workshops, or events like today. So we need your help to collaborate and move AI forward. Thank you for your time and attention, and we look forward to that collaboration.
Well, thank you, Dr. Turek. We'll jump right into the questions. The first question, outside of the program examples you've shared, are there any trends, promising areas of research, or relevant technologies in this space that will enable trustworthy AI?
So I like some of the early trends that I've been seeing in terms of building AI algorithms that are focused on adaptation. They might leverage curiosity to explore the environment and learn. There was work done on DARPA's Machine Common Sense program that built some of the foundational approaches to that bipedal robot that you saw on the video earlier. There was also Deepak Pathak, one of the DARPA risers, also showed a similar approach to building those highly adaptable AI algorithms. So that's one thread of work that I think is very promising for the future. Another thread is work done by Yejin Choi at the University of Washington, where she and her research team have developed approaches to mine these large language models, to treat them as the statistical models that they are, and they figured out clever ways to extract symbolic knowledge from those models. It turns out that if you leverage that symbolic knowledge, you can perform even better on the benchmark tasks than the large language models and do it with a much smaller model. So I think those sorts of approaches are really compelling and something to look at for how we move forward with AI system.
Great, thank you. Our next question, today the White House OSTP released a blueprint for an AI Bill of Rights to address trust in AI. How does DARPA's work relate to this initiative?
So I actually haven't seen what was released today from OSTP, so I'm not going to comment on that directly. What I will say generally is that we work closely with government partners across the entirety of government. That includes OSTP, that includes part of the DoD, that includes a broad range of transition partners. I think the DoD in particular, in terms of trustworthy AI, has been very forward-leaning in terms of defining ethical principles for AI and then starting the process for understanding how we move forward to operationalize those AI approaches.
Next question touches on some of what you just shared. Do you think there is a place for AI ethics-centered programs at DARPA?
So I think there is opportunity to get after AI ethics. I think for DoD operational needs, again, where we're facing life or death consequences, as we start building more capable, more compelling AI systems, we're going to need them to understand humans, including in terms of the values and the sorts of decisions that humans might make if they were placed in those sorts of situations. That's going to be a very long-term research problem. So that's a place where I think early investment from DARPA can help move the community.
A next question from the audience. It seems like the definition for trustworthy AI is very qualitative and subjective. What sorts of objective metrics or more quantitative means do you see as necessary to benchmark AI in the 3 categories that you have mentioned to objectively say we've arrived at trusted AI?
Yeah. That's a great question, and it turns out that this is something that the trust community has been grappling with for decades. So trust is subjective. Now, there are ways to get after measuring trust in humans, things like surveys or by analyzing their behavior. In the context of that ITM program that I talked about, that program is framed around delegated decision-making. So there's actually quantitative targets that you can look at if you review the BAA in terms of willingness of humans to delegate decision-making to another human or to an AI system. We're going to measure that in blinded ways, but that will allow us to actually quantitatively compare a human's willingness to delegate decision-making authority to an algorithm or to a human.
A next question is, how is the U.S. doing compared to its peers/adversaries in this area?
So I think if you take a look at the research literature, you'll see that the gap that we used to enjoy between the US and AI research and other countries is shrinking. That's in terms of top publications, participation at conferences. There's a number of different metrics that you can look at to understand that that gap is closing, and in some cases, it might be gone. So I don't think we can take for granted the fact that the US is going to be the leader in this area. If you combine that with the fact that competitors may not share core values that we hold as a nation, it is really important that we figure out how to sustain our competitive advantage in AI. I think we can do that by collaborating broadly across the community. I think we can do that by collaborating internationally across like-minded partners. But we have some real challenges ahead of us in terms of how we compare to other countries that might not hold the same values we do.
Thank you. Next question. How might open source data enhance decision-making and situational awareness in terms of AI?
So that's a great question. Certainly you want to leverage all the data that might be available to you for decision-making or for situational awareness. I think the AI and the machine learning community from a DoD and intelligence perspective has certainly been looking at open source data historically. There's, probably over the last decade or so, there have been many efforts that look at that sort of data. Again, one of the things to keep in mind, going back to my comments about adversarial AI, when you're collecting openly available data, open source data, you don't have control over the acquisition chain. That provides an opportunity for an adversary to pollute that data or to insert patterns in that data that might cause AI systems to react in potentially bad ways. So there's a balance there between leveraging that open source data and understanding the fragility it might bring in some cases.
Okay, we have time for one final question. Great presentation. I am curious about the status of DARPA's AI Next campaign and how that fits into the issues facing trustworthiness.
So DARPA's AI Next campaign kicked off in 2018, and it was a significant investment of the agency across a wide range of programs. That supported efforts like DARPA's Explainable AI and Machine Common Sense efforts, and programs like URSA and others that we are starting today. It's really driven AI across the agency, not just in terms of foundational AI efforts, but in terms of more applied AI efforts like you've heard about in the context of Alias. So that really provided important foundational investments. Stay tuned at future DARPA Forward events where you'll hear more about how we're going to be moving forward in our outreach to the AI community.